All right, everybody, welcome to Math with Grace. Today we're going to be working through Algebra 2, Book 10, Lessons 1 and 2, and an extra bit. Lessons 3 and 4, I won't be teaching. This is the video specific for my class. I won't be going over Lesson 3 and 4, but we will be doing something in its stead. All right, so here we go. Lesson 1 begins on page 2, and it's titled The Law of Signs and the Ambiguous Case, Part 1. Ooh, that alludes to a Part 2. Very exciting, okay? It says, thus far in this course, when we were given information for a triangle that has two sides and an opposite angle, using the law of signs, we could find the missing parts, right? But that's not always the case. Side angle information can define 0, 1, or even 2 triangles. Therefore, it's called an ambiguous case because the lack of information that they're giving you shows that we can actually produce more than one triangle. It's why we don't do combinations like side. If a triangle has all the same sides, do they have the same size angles, right? So we don't define a single triangle as do the combinations like that, okay? So these types of triangles can define 1, 0, or more than one. So let's take a look at the rules for deciding whether there's going to be a triangle, 2 triangles, or none with the information that we've been given. So here's one thing to consider. They do not actually mark any of these with H, which is the height of a triangle. So I drew it in here on number 5. Remember, the height of a triangle is from the vertex to the base, a perpendicular line, okay? That represents the height of a triangle. So when they say that A is less than H, that is what they mean, okay? If A is less than H, so looking at number 5, but talking about this particular incident, okay? If A, which means this side, is less than this height, then there are 0 triangles because that is not possible, right? Here's angle A. Side A is opposite that. Side A could be the height, but it can't be shorter than the height of the triangle, right? Because here's where the vertex is, where A and B come together, or where A and C come together. A cannot be shorter than H. If A is less than the height, then we cannot make a triangle, right? That's why they show just a piece of it, because it's not big enough to fill in the whole side. That's not a triangle. So it makes 0 triangles. Number 2, or example 2, states that A is equal to H, like I was mentioning over here, right? A and H are the same thing. There is one triangle. It's a right triangle that is created, okay? Then here are situations where there are 2 possibilities for triangles, okay? A is greater than H, okay? So H in this case would be like right here, okay? Well, no, not really. H is outside of this triangle, or H is technically this way, I guess. Okay, so A is greater than H, and A is less than B. So A is shorter than B. There are 2 possibilities. So these 2 drawings represent the 2 possibilities. Because they're only giving us one angle, it just isn't enough information, okay? To know whether it's going to be a triangle like this or a triangle like this, okay? So there's 2 possibilities. When A is greater than H, but less than B. And then we have one triangle where A is greater than H, and A is greater than B, okay? If A is greater than H and greater than B, then there is one triangle that can be created, all right? So it says the number of triangles possible for a side-side angle data depend on the relationship of side A to the height of the triangle and side B. And they've summarized it in this chart, which is very useful, and I suggest referring to it often. Let's take a look at example 1. Trying to keep the chart on the page here. Determine how many triangles exist for each set of data. There's 1, 2, 3 examples in example 1. I don't like it when they write it this way, but hey, what am I going to do? Triangle here, in number 1, angle A is 45 degrees. Side B is 12, side A is 14. Okay, so A is less than B, okay? Because it says here, because A is greater than B. Because A is greater than B, it's not necessary to find the height. We don't need to know what the height is of the triangle. The data corresponds to number 5, okay, where A is greater than B, right? That's the only one where A is greater than B. Therefore, there's one triangle, okay? And they have this broken down in this box here between acute and obtuse. Obviously, this is an acute angle because A is less than 90 degrees, all right? Angle number 2, angle A is 25, again, acute. B is 15 and A is 8. So A is less than B, okay? So now we have to think of, its relationship to the height. Now, the sine of angle A is equal to the opposite over the hypotenuse, right? So it's equal to h over b. That's where they came up with this formula. That's why I drew this in over here, okay? So the sine of angle A is equal to the hypotenuse over b, okay? So they put in the information that they knew. A is 25 degrees, so the sine of 25 is equal to h, because that's what we're looking for, over 15. You multiply both sides by 15, and you get the height to be about 6.3. So now we know that A is less than B, okay? A is less than B, but A is greater than the height, because 8 is greater than 6.3. So there are 2 triangle possibilities with this amount of data given, okay? And part 3 of example 1, angle A is 130 degrees. I'm going to slide up here a little bit. That's an obtuse triangle, okay? B is 21, A is 20. So A is less than B. So in an obtuse triangle, if A is less than B, okay, 0 triangles are possible, right? We cannot actually make a triangle with the data given. All right, let's take a look at these problems together. All right, we're in Algebra 2, Book 10, Lesson 1. We're on page 3. We are doing these 3 problems together. And the instructions tell us to determine how many triangles are available. I've kept my little summarization chart here off to the side so we can take a look at it as we go. All right, for number 1, A is equal to 58 degrees, B is equal to 10, A is equal to 9. A is less than 10, and angle A is an acute angle. So A is less than B. So just looking in this chart, there's only one where A is less than B, but we need to know, is it greater than, there's one here that A is less than B as well, but we need to know for both of them the height. So we need to calculate the height. I wrote the formula for it here. So the sine of 58 degrees is equal to h, which is what we're looking for, over b, which is 10. So we need to multiply both sides by 10. So we're doing the sine of 58 degrees times 10. Let's see here. Oop, clear. So I went ahead with the sine of 58. I needed to check my calculator. One of the calculators I used at some point this week was misleading me, which means I need to change some of the settings, but it's not this one. So the sine of 58 degrees, I've calculated. We're going to times that by 10 or just move the decimal place. It's 8.48. I'm going to say 8.5. Okay, so The height is 8.5, which is less than A. So A is less than B, but it's greater than the height. So there are two triangles available, or possible, I guess, is a better word. Okay, let's look at number 2. For number 2, angle A is 127 degrees, B is 32, A is 24. A is an obtuse triangle. So we need to find out, is A less than or greater than B? A is less than B, so there are 0 triangles. Obtuse is about the easiest one to do. Number 3, angle A is 145 degrees, B equals 3, and A equals 27. So again, we have an obtuse, but this time A is greater than B, so there is 1 triangle available. Okay, let's take a look at the next 3. All right, for number 4, we have angle A as 37 degrees, B is 14, A is 12.5. All right, we have an acute angle. A is less than B. So here's my less than B, less than B. I've got to solve for my height. So the sine of 37 degrees is equal to height over 14. Okay, multiplying both sides by 14. So we have, make sure you can see that, okay. We have the sine of 37 degrees, close parentheses, times 14, gives us 8.425, but I'm just going to say 8.4. Okay, 8.4 is less than 12. So A is less than B, okay, and A is less than the height. So that tells me the height is less than A. So A is greater than the height. So there are 2 triangles. Goodness gracious. A is less than B, but A is greater than the height. So there's 2 possible triangles that could be created from the information given to us. Okay. Number 5. Always check your word. Number 5. A is equal to 112 degrees. Obtuse triangle. B equals 27, A equals 25. So we have an obtuse triangle where A is less than B. Okay, so there are 0 triangles. Probably better like this, right? A is less than B, so there are 0 triangles. Okay, last one. Number 6. A is equal to 48 degrees, B is 8, A is 16. Okay. Acute triangle where A is greater than B. A is greater than B. A is greater than B, and A equals the height. But the thing is, we don't really need to calculate it because they're both just 1 triangle. Okay? We don't need to figure out what the height is because either way, it would just be a 1 triangle thing because A is greater than B. Okay? 1 triangle. That's all they're asking for here. Make sure, as always, I don't expect anybody to memorize these things, but make sure you either take note of it on a note card so you can use it throughout your work, or mark this page so you can come back to it when necessary. All right, go ahead and finish the rest of lesson 1 and meet me back here for lesson 2. Lesson 2 begins on page 5, and it is titled Conic Sections in Analytic Geometry, Hyperbolas. So the intersection of a plane and a double cone creates a hyperbola. So the plane is this gray bit crossing this double cone. So it makes a curve and a curve, okay? When the plane is parallel to the central axis. So the central axis being the straight line that runs through the very points, okay? And is perpendicular to both of the bases. The geometric definition of a hyperbola is this. Okay, we can read it together. A hyperbola is a set of points in a plane such that the difference of the distances from the 2 fixed points to any point on the hyperbola is a constant, the focal points. The 2 points are called the foci, which is plural for focus, okay? Basic definition of a hyperbola. Let's keep looking down the page here. So, when we do this, just like when we were doing ellipses, okay, A is associated with the longest axis the major axis, right? And B is the minor. But this case, we don't really have a major and a minor. It's just that A is always going to be associated with the longest axis. So the A would be this way, and the B would be this way in that case, okay? Here are the possible equations for a hyperbola. These are the standard equations with the center at the origin point, where the x-axis is the longest, okay? Then you have x squared over a squared minus y squared over b squared equals 1. That's a horizontal hyperbola, okay? A vertical hyperbola, where y is the longest axis, then you have y squared over a squared minus x squared over b squared equals 1, okay? Note the two equations differ only by the position of the x and the y. Everything else is the same. The minus differs it from an ellipse, right? And helps us to identify that it's not an ellipse, but a hyperbola, okay? The transverse axis, or the longest axis, is perpendicular to the conjugate axis, which is the shorter one. This is perpendicular to this, okay? Where did I leave off? Okay, the foci are inside the curves of the hyperbola. Okay, as you can see here, they're inside the curves of the hyperbola. Each hyperbola has a pair of asymptotes, which are values the hyperbola approaches but never crosses. The dashed rectangles in the graphs below, of course, it's on the very next page, so we can't look at it while we're reading, represent the intersections of the transverse and the conjugate axis. Axi? Let's turn the page. It says the transverse axis endpoints, negative a and a, intersect the vertices of the hyperbola. Okay, so this is this point, which is the vertices of this side, is negative a comma 0. This point here is at positive a comma 0. Okay, the conjugate axis endpoints are at distance negative b and b. Now, that's here and here. Those points are not that important to me. This box I don't need to see, but if you look real close, and you'll probably have to look in your own book because it's so light in this book that it's probably not coming across on the screen, that I didn't even notice when I was prepping for this a couple days ago. I didn't even notice them on here, but there's a very, very fine dotted line that goes like this. And there's another one that goes like this. That is the asymptote. That I want to see on your graph. If you don't plot this box, I really couldn't care less, but I definitely want to see the asymptotes, okay? So you might be asking, well, how do you find those? Well, here we go. Each hyperbola has two asymptotes defined by y equals plus or minus b over a times x, which is the equation for a line, okay? Y equals plus or minus b over a. B over a creates our slope, okay? Tells us how far we go up and how far we go over. Or in case of the negative, how far we go down, how far we go over, x. So we're starting at the origin and we're going up. In this case, even though it's so fine, you went up 2 over 1. So for this equation, my b is a 2, my a is a 1, because we went up 2 over 1. So if you have a drawing, it's an easy way to determine what the a's and b's are. But it's just the slope of the line. You put a dot, you draw your line, draw your dotted line. You go down 2 over 1, you draw your dotted line, okay? Those are what I want to see. The box, it's not really necessary for me personally. And then you also need to determine the foci. Now they've got a bunch of words here. It says the important part, I did not highlight it. Let me do that real quick. All right, so it says the foci are on the transverse axis. Remember, the page before said the transverse axis was the longest one, at a distance of negative c and c from the center. And in this case, we're talking about the origin point. We're not going to be moving these just yet. So it's going to be 0, comma c and 0, comma negative c. Those are my focal points. And here's how you find it. Slightly different than the ellipses that we were doing. The foci are at plus or minus the square root of a squared plus b squared. That's how we determine the foci. Okay, so let's take a look at example 1 down here. It continues on to the next page, but it says write the equation for a vertical hyperbola. So I already know my y squared is coming first, centered at the origin with a equals 3, b equals 4. So here is the setup. We already know the y squared will be over the a squared because it says it's a vertical hyperbola. Then we fill in the a squared, b squared. I don't think they ever actually square it, but you should. And then they figure out the foci. Again, they do their foci kind of weird, but this is the formula for the foci, okay? I mean, it's not kind of weird. It's just they don't do the work. They just skip ahead. So it's plus or minus 5 is the foci, okay? So let's move up to the top of page 7 to see how they've graphed it. So they made the box. Again, I've told you the box is not wholly necessary. We knew that a was 3, so if we went to 0, 3, put a dot, and 0, -3, put a dot, okay? Then that is our vertices for this hyperbola. What they don't show me here, so they just say asymptotes drawn through the diagonals, but they don't show you how to calculate it. So let's, again, do that here. So remember, the vertices are going to be at y equals plus or minus b over ax, okay? That's for a horizontal. For a vertical hyperbola, it's a over b. So a over bx is what we are using for a vertical hyperbola, okay? So plus or minus a over bx. My a was 3. My b is 4. So my asymptotes, one of them is going to be at y equals positive 3 over 4x. So you're going to go up 3, 1, 2, 3, over 4. Boom. That's this spot here. You're going to use a ruler, a straight edge, and you're going to draw a dotted line all this way. So at this point, us personally have graphed this dot, and this dot. We're going to draw this dotted line in. Then we're going to go down 3 over 4 and put a dot here, and we're going to draw that dotted line in. So for us, we have our 2 asymptotes and our 2 vertices, and that's all you really need to just go swoop and swoop, okay? Knowing that our hyperbola will run and get closer and closer to our asymptote, but never cross it, okay? And then we can graph our foci, which we calculated to be at plus or minus 5. Since it's vertical, it's at 0, plus or minus 5, and we can put in those 2 points. All right, let's take a look at example 2. For example 2, it says provide the equation for a horizontal hyperbola with a transverse axis, so our longest one, a length of 7, and a conjugate axis, the length of 5. All right, and it says then determine the foci rounded to the nearest tenth. Okay, the transverse axis is equal to 2a. Remember, it's the length, so the length is 2a's. So a is 3.5, okay, half of 7. The conjugate axis is also 2b's, so the length of b is 2.5. Not the length, but the b is 2.5. So we can now set up our equation. Horizontal hyperbola tells me that my x goes first. So it's x squared over 3.5 squared minus y squared over 2.5 squared equals 1. To figure out, so they asked us for the equation, then they asked us for the foci. So the foci, remember, is the square root, the square root of a squared plus b squared. So we actually need to square them and then take the square root. So plus or minus the square root of a squared, which is 3.5. So 12.25 plus b squared, which is 2.5. or 6.25. And then we take the square root of the, oh, this one I didn't have to shift, answer equals, so it's approximately 4.3, right? Which is what the book says, but I wanted to work through it with you. So we know that the foci are at 4.3 comma 0 because the x squared comes first. The foci calculation goes in that point, and negative 4.3 comma 0. All right, so let's take a look at these 4 problems. So we are in Algebra 2, Book 10, Lesson 2. We're on page 7. I took this part of my graph paper to just make a quick note of all the information regarding hyperbolas that we know so far anyway. Horizontal hyperbola and its asymptotes, a vertical hyperbola and its asymptotes, and then they both have the same formula for the foci, so I just kind of put it in the middle. If you haven't made a note like that already, I would suggest it. Problem number 1, the instructions read, write the equation for the hyperbola centered at the origin, determine the foci of each hyperbola, and then sketch 2 and 4. Okay, so problem number 1, we have a horizontal transverse axis. Okay, so immediately we know it's this setup here, and my a is 4, my b is 3. So I can write my equation now. It's going to be x squared over a squared, which is 16, minus y squared over b squared, which is 9, equals 1. All right. There is the equation of my line, and then it wants me to find the foci. So for my foci, it's going to be plus or minus the square root of 16 plus 9, right? Which is the square root of 25, which equals plus or minus 5. So because this is a horizontal and the x comes first, my foci are going to be at 5 comma 0 and at negative 5 comma 0. All right, and that's the information that they asked us for. For number 2, we have a vertical transverse axis. A is 3, b is 2. Vertical tells me I've got this situation going on here. Okay, so my equation is going to be y squared over a squared, which is 9, minus x squared over b squared, which will be 4, equals 1. That's the equation, right? I might as well determine the foci, and then we'll determine the asymptotes, and we'll sketch it. So for my foci, I have plus or minus the square root of 9 plus 4, which is plus or minus the square root of 13. Now, usually I don't encourage decimals, but since we have to graph this, we're going to go ahead and figure out what this is. So the square root of 13 is equal to 3.6, we'll say. So this time I'm dealing with a vertical transverse. My y is first, so my foci is at 0 comma 3.6 and 0 comma negative 3.6. Okay, those are my foci this time. Now, to graph it, I need to know my asymptotes. Okay, the boxes, whatever, but the asymptotes are what help me graph. Being a vertical hyperbola, this is the formula for the asymptotes. So asymptotes are going to equal plus or minus a over b x, or plus or minus a, remember, was 3, b is 2, x. Okay, so now let's set up our graph. You don't really need that big of a graph because here we are, right? Now remember, for our vertices, it's going to be at 0 comma 3. So 0 comma 3 and 0 comma negative 3. Okay, those are the vertices of our hyperbola. Then we're going to graph our asymptotes. Our asymptotes are at plus or minus 3 over 2x. So plus 3 over 2x is up 3. So 1, 2, 3 over 2. That's enough data for me to go ahead and plot this. I have my little eraser here, or my little ruler today, so I'll have to deal with this one. And remember, this is a dotted line because it just shows us that our hyperbola is not going to cross that point, right? And then the other asymptote, because we have 2, is down 3. So 1, 2, 3 over 2. I hope I'm hitting this right. This big ruler is hard to see past. Hey, pretty good. All right. So it's going to look like this for my asymptotes. Okay. Now that my asymptotes are drawn in, we can sketch our hyperbola. It's going to look like this. And I didn't make a very big chart, so it's just kind of there. All right. And there we go. We've sketched it. Rough sketch, but a sketch nonetheless. All right, let's take a look at the next 2. Problem number 3 reads a vertical transverse axis that is equal to 10. So 2a equals 10. And a conjugate axis that is equal to 5. So 2b's equal 5. Vertical tells me that my y comes first. So I'm going to have my y squared over, we'll calculate it in a second, minus x squared over b squared equals 1. Okay. 2a equals 10. Okay, so a is equal to 5, so a squared is 25. 2b is equal to 5, so b is equal to 2.5. And what did we say 2.5 was squared? Was like 6.25? Yeah, 6.25. Okay, so b squared is 6.25. Okay. We are just figuring out the equation, which we've done here, and then we want to find the foci. So the foci is plus or minus the square root of a squared plus b squared. Okay, so 25 plus 6.25, which is the square root of 31.25, right? The square root of 31.25. Which is what? That part I need help with. So the square root of the answer is equal to 5.59 or 5.6. Okay, approximately. Now, because this is a vertical hyperbola, this is the y value. Remember, plus or minus. Okay, so it's at 0, 5.6 and 0, negative 5.6. Those are our focal points, okay, for number 3. Okay, so we got our focal points, we got our equation. Let's look at number 4. For number 4, we have a horizontal transverse axis, so my x squared comes first. My a is 4, my b is 2. So I have x squared over a squared, which is 16, minus y squared over b squared, which is 4, equals 1. Equation done, right? My foci are at plus or minus the square root of 16 plus 4, or plus or minus the square root of 20, which we need to calculate here. So we have the square root of 20 is 4.5. We're going to round this 4 based on that 7, so plus or minus 4.5. Now, because this is a horizontal, that is our x value. So I've got 4.5, 0 and negative 4.5, 0. And I just realized I forgot to plot my foci over here on this chart. Remember, it was at 0, 3.6, so 1, 2, 3. It's a little bit more than half. And negative, same thing. So there they are, plotted. Don't want to forget to plot all our points. Now, to figure out what we need for problem 4 to graph it, because it asks us to graph number 4, we need to figure out our asymptotes. Okay, now this is a horizontal hyperbola, so the horizontal uses plus or minus b over a. Plus or minus b, which was 2, over a, which is 4x, or plus or minus 1/2 x, right? We need to reduce. So there are our asymptotes. Let's get our graph ready. So remember, our center is at the origin point, okay? Our vertices are at this. To find our vertices, it's our A, and since our A is under the X, it's going to be at 4, 0, and -4, 0. Those are our two vertices. So 4, 0 is 1, 2, 3, 4. -4, 0, 1, 2, 3, 4. That's the vertices of our hyperbola, okay? Then we're going to graph the asymptotes, plus or minus 1/2 x. So I'm going to go up 1 over 2. Okay, you could do it twice, up 1 over 2. Since I got a super giant eraser ruler today. Sorry, I don't have my little clear one. Makes it easier to see what we're doing. Okay, there's one asymptote. And then the second asymptote is -1/2 over 2. So down 1 over 2, down 1 over 2. And we're going to line it up as best as I can't see. Okay. And it's going to be about there. Okay. Oop. I have my two asymptotes, all right? I can draw my hyperbola. Remember, it's just a curved line that gets close to my asymptotes on either side. Now, let's not forget our foci. Our foci is at 4.5, so 1, 2, 3, 4.5. And at -4.5, which would be there. All right? So we have our asymptotes. Again, the box that the book shows is really not that important. The asymptotes are what we use to determine where the hyperbola goes. I mean, we can calculate points if we wanted to, but this just makes it easy. So we have our asymptotes, we have our vertex, and we have our foci. All right? Those are the most important parts of our hyperbola so far. All right? That's it then for lesson 2. Go ahead and finish the review section for lesson 2 and meet me back here for our added section. We're not going to do, as a reminder, lesson 3 and 4. So let's just meet back here for what we are going to do. So what we are going to work on is called applications of fractions. This I am borrowing from last year's Algebra 2 curriculum. They changed the curriculum this year. But this is not really something that they go over in the new curriculum, but I feel like it's pretty important. So I will be providing you this section of information in class, but let's go ahead and dive right in. So this was technically in book 1005 of last year's curriculum of the other Algebra 2, and it was section 4 called Application of Fractions, okay? And so it says the most exciting and rewarding part of your studies in algebra occurs when you are able to use your skills to solve word problems that without algebra could seem impossible. Certain types of motion problems, most mixture problems, and most work problems involve the fractions that we have been working with. It says in this light unit, but obviously that doesn't pertain to us specifically, but we have worked with fractions throughout our Algebra 2 career, so this isn't exactly out of left field. Let's take a look at motion problems. So as you've already learned, linear motion problems are based on the formula distance equals rate times time. D equals R times T. So when solving a motion problem, a sketch is often helpful. You know how much I love sketching things. A table can be used for organizing information, which will be very useful as well. And remember the 4 steps for solving word problems. Identify the unknown number and choose a variable for it. Write an equation or an inequality. Solve the equation or the inequality and identify your answer, label it, and check to see if the conditions stated, or if it fulfills, the conditions stated in the problem. Is the answer you solved for the answer that they are wanting, or do you need to do another step? Is basically what number 4 says. Taking a look at the first example, they call them models instead of examples in the old curriculum. But model 1 says 2 boys who lived 14 miles apart, okay, start walking or sorry, at noon, start walking towards each other. Exact same time, they're walking towards each other. One is walking at 3 miles per hour. One is walking at 4 miles per hour. In how many hours will they meet? Okay, well, here's the time walked is what we're looking for. How many hours will they meet? So our x is going to be the time. Remember, distance equals rate times time. So the first boy is walking at a rate of 3 miles per hour in X amount of time. They're going to be walking the exact same time. Now, they're not going to be walking the exact same distance, right? But they will be walking the same amount of time. They both left at noon, and whatever time they meet each other is going to be exact same for both. So he walks at a rate of 3 in X amount of time, so his distance is 3x. The second boy walks 4 miles per hour, so his rate is 4. His time, again, is still x, and so his distance is 4x. 3x plus 4x, since they're meeting, he's walking a little faster, so they're meeting somewhere here-ish, let's say. 3x plus 4x equals 14 miles. Okay, so they set up that equation here, and then they solved for x to find out that x is 2. So what does that mean? That means in 2 hours, they will meet. Okay, now this question could have asked, how far will boy 1 walk? How far will boy 2? How far will they each walk? Had they asked how far they would walk, which is what they've kind of done here, they've checked, right? They're just checking their math. If they asked us how far they walked, that would be number 4, right? We've answered it and labeled it, but is that what the question is asking? If it asks us how far they walked, then our x equals 2 is not quite the right solution that they're asking for, but it's the only one we can solve for. But then we can go back, right? So 3 times 2 is 6, so he's walking 6 miles. 4 times 2 is 8, so he walked 8 miles. All right, so there's more information than we can find from the information that we solved for, but we just want to make sure we are answering the correct questions. Okay, let's go to the next page. So at the top of what they have listed here is page 40. You can see it here. It says the distance formula can be used to find the rate or time as well as the distance, because rate equals distance over time and time equals distance over rate. Fractions are involved when those formulas are used. So model 2, example 2. In still water, George's motorboat goes 4 times as fast as the current in the Palomino River. Okay? He takes a 15-mile trip up the river and returns in 4 hours. Find the rate of the current. So we want to know how fast, that's what we're looking for. X equals the rate of the current. All right? So he's going 2 different ways. He's going downriver and he's going upriver. Downriver, meaning with the current. Upriver, meaning against the current. Okay? With the current, against the current. So let's read about what does the story problem tell us about the current. Well, in still water, which means no current at all, the boat moves 4 times as fast as the current in the river. So we know that in still water, or downriver, or upriver, in still water, the boat moves 4 times as fast as the current. So when he's going downriver, the boat's going to move 4 times as fast as the current, plus the current is pushing him. So that gives him that speed of the current. Upriver, the boat moves 4 times as fast as the current, but the current is pushing against him, so we subtract the rate of the current. Okay? So downriver, we're going with the current, so we add it. Upriver, we're going against the current, so we subtract it. Okay? The distance is 15 miles both way. Downriver, it's 15 miles. Upriver, it's 15 miles. Okay? So to solve for time, the time, remember, where's it? Here it is. Time equals distance over rate. So the time is the distance over the rate, which is altogether 5x. And same here, time is distance over rate, which altogether here is 3x. Now, we know that our times equal together 4 hours. Okay, he takes 15-mile trip upriver and returns in 4 hours. So he goes there and back in 4 hours. So our time there, which they reduced to 3 over x, okay, plus our time back, which they reduced to 5 over x, is equal to 4. They multiplied each term by x and got 3 plus 5 equals 4x, or 4x equals 8, so x equals 2. Okay, we're partially there. They want to know the rate. We just solved for the time, okay, or a time variable. They check their work, okay. But what have we solved for? We've solved for the rate of the current. Oh, and that's what they wanted to know. Sorry, that is what they wanted to know, the rate of the current. So we have solved for the rate of the current. So they don't want to know how fast he actually went downriver or how fast he went upriver, which we could totally find. But they want to know the rate of the current, which we solved for as 2 miles per hour. We know it's miles per hour. Why do we know it's miles per hour? They don't actually tell us. Well, miles per hour because he's going miles and we're talking about hours. So miles per hour. Okay, so the current rate is 2 miles per hour. And that's how you would write it, miles per hour. It's our unit of measure, right? Now, this book, this older curriculum is set up slightly different. So they teach a topic and then there's problems. So there's like a couple pages worth of problems here. I will hand out in class. So we're going to do a couple together, but then the rest is like the homework part, okay? So let's take a look here at number 1. So for problem number 1, we have that one automobile travels 10 miles an hour faster than a second automobile. If the first automobile travels 80 miles farther than the second automobile, which travels 240 miles, what will the rate of each automobile, what will be the rate of each automobile if they travel for the same amount of time? So we are going to set up a chart similar to this, right? So we have rate, time, distance. Mine are a little bit more basic than the book, but that's okay. Whatever gets you through it, right? So automobile number 1, and we have auto 2, right? That's what they gave us. So we've got our chart started. Now, it says one automobile travels 10 miles an hour faster than a second automobile. So which one is the slowest? Well, it's automobile 2, so that becomes our x. And automobile 1 is 10 miles an hour faster. Well, that's x plus 10. That's how we represent 10 miles an hour faster. Then it says here, if the first automobile travels 80 miles farther than the second, which traveled 240 miles. So the distance of the second is 240. So the distance of the first is 80 miles more. So that's 320. Okay. What will be the rate of each automobile if they travel for the same time? So our time is the same. Time of this is, sorry, I don't know why I put a T there. Time of auto 1 is equal to time of auto 2. So since we already have a variable here, how do we represent time? Remember, at the top of this page here, time is equal to distance over rate. So our time is equal to 320 for the automobile 1 over x plus 10. For automobile 2, it's 240 over x. All right. Now, they gave us the formula that we're going to use. The time of automobile 1 is equal to the time of automobile 2. That's what we're going to set up. So 320 over x plus 10 is equal to 240 over x. Now, if you remember what we have here, then we can solve this very easily. Remember, when we have a fraction equal to a fraction, it sets up a proportion. And proportions, we cross multiply. So 320, goodness gracious, 320x is equal to 240 times x plus 10. Okay? So 320x is equal to, make sure you distribute, 240x plus 2,400, okay? We need to combine our like terms, so we're going to subtract a 240x from both sides. We already know what that is because it tells us right here. So we have 80x's is equal to 2,400. We can subtract, or we're going to divide both sides by 80. Okay, but we can subtract a 0, so we know that this is 30. Now, 30 though is what? 30, because they want to know the rate, what will be the rate of each automobile. Make sure you're answering the question. Well, x equals 30, so auto 2 is going 30 miles per hour. Auto 1 is going 30 plus 10, or 40 miles per hour. Okay, so that's what they want to know. We solved for one thing, but we need to know multiple things. All right, so the basis of this rate or distance, motion problems, okay? The best way to do it is to set up a graph. It's how I like to do it. Sometimes I draw a drawing, but this chart is what helped us get all of our parts together and then solve this problem, okay? So this chart is the best step in solving these problems. All right, let's take a look at one more. All right, for problem number 2, we read that a freight train travels at 30 kilometers an hour. If the freight train is 300 kilometers ahead of the express train traveling at 55 kilometers per hour, how long will it take the express train to overtake the freight train? So we've got two trains, right? But we have a rate and a time and a distance for both. We have a freight train and we have an express train. I'll just call it the X train. It's X train, okay? Now, what information did they give us here about these trains? A freight train travels at 30 kilometers per hour, so that's its rate, 30. If the freight train is 300 kilometers ahead of the express train, so who is least far away? Well, that's the express train, so we're going to make that one X. And so the distance of the freight train right now is X plus 300, right? It's 300 kilometers ahead. And the express train, so the freight train is 300 kilometers ahead of the express train, which is traveling at 55 miles per hour. All right. How long will it take the express train to overtake the freight train? What time, since they're both starting at the same point, or at the same time, right? Here is my express, or sorry, I called it XT. My express train, and 300 kilometers ahead of it is the freight train. So this is the 300, but they both then take off at the exact same time. How long is it going to take for the freight train to overtake the express train to overtake the freight train, okay? But remember, so time equals distance over rate. So this is X plus 300 over 30, and this is X over 55. Now, again, they started at the same time, so their times are equal. Again, the time of the freight train is equal to the time of the express train, okay? So we can set those things equal to each other again. So X plus 300 over 30 is equal to X over 55. Cross multiply because we have a proportion. So I'm going to have 55 times X plus 300 is equal to 30X. We have to distribute 55X plus, what would that be? I always forget. 55 times 300 is 16,500 equals 30X. Okay. Now, we have to do some switcherooing here, right? So we need to add 30 to both, or sorry, subtract 30 from both sides. Minus 30X. But we also need to subtract this 16,500 from both sides. Now you might be thinking, how are we going to do this now that we have a negative number, right? Because we can't have a negative time, because that's not how time works. There's no such thing as negative time. But what we're going to do is we're going to do the math, and our time is going to be a positive number of minutes. It's just what it is. I know it's going to be negative, but we can't have a negative time, so our answer just becomes a positive number. So 16,500 divided by 25 is 660. Now, that doesn't quite make sense, because 660 what? Okay. But if you remember what our x is the distance that the express train travels. But the question is asking us, how long will the express train take to overtake the freight train? So it's going to be x over 55. We want the time. So this time, what we solve for isn't exactly the answer we're looking for. So if we take 660 divided by 55, we'll get the time that it actually took. And that is 12 hours. It's going to take the express train 12 hours to overtake the freight train. Okay? 12 hours to beat that freight train. But it will eventually, because it's going not incredibly faster, right? It's only going 25 miles per hour faster, and it's going to take 12 hours to get there. All right? So that is the basis of motion problems. You're going to set up this chart, and then reading the question, figure out what is equal to what, or greater than or less than, or however the problem has it set up. And then solve. All right? So you would finish the rest of these problems and then meet me back for the next topic, right? There's 3 topics to this add-on section that we're doing. So meet me back here for the next topic. So the next topic begins on page 43 of this printout, this handout, and it's called mixture problems, okay? Now, a mixture problem is a problem dealing with quantities containing the same elements, but combining different amounts of those elements, okay? They have these little box things drawn up. This is not the exact way. I mean, the next page is a bit more clear. This is kind of an interesting setup. But the table in the chart to organize your data is very important. It says sometimes more than 2 quantities are combined, and sometimes quantities are removed. So we're combining 2 or more, and sometimes we are combining some and removing some, okay? That is just the way mixture problems work. So going on to page 44, it's model number 3. Now, model number 3 of this section, not obviously of this topic. So a nurse is asked to dilute with water 3 ounces of a certain medicine, which is 80% pure medicine. So it's already 80% medicine. She is to make a mixture which is 20% medicine. How much water should the nurse add? And then it says, hint, the water is 0% medicine, right? Because it's just water. Let's hope there's no hidden medicines inside. So they have set up their variable. X is equal to the ounces of water to be added. How much water are they adding? That's what they're asking. How much water should the nurse add? We know it's ounces because we're starting with ounces, right? So setting up the chart, here's how I like to set up my chart. I would write the 80% medicine, and underneath that, I have 3 ounces at 80%. Remember, 80% written as a decimal is 0.80. Okay, so you have 3 ounces at 80%. Plus X amount of ounces at 0%, because our water, that's what we're adding, is no medicine. But we need it to equal 20% medicine, and then how much are we going to have of that? Well, we're going to have the 3 ounces that we started with plus the amount of water that we added. So it's 20% times the quantity, that's important, parentheses, 3 plus X, because that is going to be our total number of ounces once we've added our water. Then they remove the decimals, which is whatever. So 3, I probably wouldn't do that when I do the problem, but hey. 3 times 80 plus 0, because 0 times x is 0, is equal to 20x plus 60. So 240 is equal to 20x plus 60. They subtract 60 from both sides and then kind of rewrite the problem so their variable is on the left. So 20x is equal to 180, and therefore x is equal to 9. Now, what was x? Remember, x was the amount of water that we needed to add. So they've checked their math, and so then they write the answer. The nurse must add 9 ounces of water. So you could have written 9 ounces in your answer. I need your unit of measures. That's important, okay? So she added 9 ounces of water. Let's take a look at example 4, model 4. An automobile radiator is full of a 15% antifreeze solution. If its capacity is 16 quarts, how many quarts must be replaced by a 90% solution to give 16 quarts of a 65% solution? So we're looking for the number of quarts to be replaced. So the initial solution is 15% and 16 quarts, right? We need to drain out 15%, and how many quarts do we need to replace? We need to take out some of these, and then we need to add a 90% solution at the same amount of quarts that we took out, right? We need 16 at the end. So whatever amount we take out, we need to replace with the 90 so that we can have a 65% solution. All right, so 15% times 16 quarts minus 15% times X amount of quarts plus 90% of X amount of quarts equals 65% of 16 quarts. The top of page 45 is the conclusion, or the rest of this problem. Again, they remove the decimals on all of the parts, okay? And then they multiplied, combining their like numbers, and find that X is equal to 10 2/3 quarts, okay? If you left it as an improper fraction, that would have been fine as well. And then they check their work because they're diligent students, right? But here it is, 10 2/3 quarts must be replaced to end up with a final solution of 65%, 16 quarts, okay? It says the fractions involved in most mixture problems are decimals because we're dealing with percentages, okay? And percentages cause decimals. Now, I don't normally just remove the decimals like that, but I suppose you could. Calculators make decimals fairly easy, so I don't normally do that. But let's take a look at 2 of these, problem 11 and 12. And we'll work through these together, okay? Solve the mixture problem, showing all your steps. It says a grocer bought some walnuts for 90 cents a pound and some pecans for $1.20 a pound. If he mixed them for a 90-pound mixture worth $1.10 a pound, how many pounds of walnuts did he use? Okay, well, let's see. So we have walnuts, and we are adding pecans, right? Because we're making a mixture. And together, it's going to be a mixture. That's what we have going on here. This is the setup. And if you can get to that point, you should be able to do the rest. Okay. So how many pounds of walnuts did he use? That's obviously our X because we don't know, right? But they are 90 cents a pound. So we have 90 cents times X amount of walnuts because we don't know how many they were. And a pound, so 90 cents a pound, and some pecans for $1.20 per pound. Okay, so we know we have pecans and that they are $1.20 per pound. But do we know how many pecans there are? No, we don't. It says if he mixed them for we'll come back to that in a minute. If he mixed them for for a 90-pound mixture worth $1.10 a pound. So our mixture is $1.10 times 90, right? Because we have 90 pounds of it. How many pounds of walnuts did he use? We gave walnuts our X because that's what they're asking for. But we don't know how many pecans there are either. But we kind of do, okay? Because we know that pecans plus walnuts equals 90 pounds. So I'm going to write it over here. Pecans plus walnuts equals 90 pounds. And walnuts, we already decided was X. So I'm going to subtract or erase my W and put an X. To solve for the number of pecans that we have, we simply solve for P, which means subtracting an X from both sides. So our pecans are equal to 90 minus X, right? The entire mixture, taking away the walnuts, will tell you how many pecans we have. So many of the problems are like this, okay, where technically we would have two variables, but these are related in a way. And because we know pecans plus walnuts is 90, we can solve for pecans as 90 minus X. All right, and then we can solve our problem. So again, I don't normally remove the decimals, so it's just going to be 0.9x. I will remove the dollar signs for now. Is $1.20, or can you see this calculator? 1.2 times 90, because we need to distribute, right? Not equals. Why did I write equals? Plus 108, okay? Minus 120x is going to equal 1.1 times 90, which is 99. Okay, there's our setup. Let's combine our like terms. So we have a negative 1.2 plus 90 gives us a negative 0.3x is equal to, if we subtract 108 from both sides, 99 minus 108 is a negative 9. Okay. Oh, I shouldn't have erased that. Negative 9 divided by 0.3 tells me that my x is equal to 30. Okay, now what is that I solved for, though? I know why this is being so weird. Here we go. X is equal to 30, right? Well, what did I solve for? I solved for the amount of walnuts. So he needs, how many pounds of walnuts did he use? He used 30 pounds of walnuts. Okay, 30 pounds of walnuts. Now, the question doesn't ask how many pounds of pecans. We could totally figure that out. But it doesn't ask that, so we don't need to do more than is necessary. So 30 pounds of walnuts is what we solved. All right. Number 12. If a dairyman has 300 pounds of milk testing 3% butterfat, how many pounds of skimmed milk, which is no butterfat, must he remove to have the milk testing at 3.6% butterfat? Okay, so we have a 3% butterfat minus 0% butterfat to get to 3.6% butterfat. That was our, remember our walnut pecan mixture? This is our basic setup. Okay, now let's throw in the information that we know. We have 300 pounds at 3%. So 300 pounds, and how do we write 3% as a decimal? Well, 0.03, right? Minus X amount of pounds. How many pounds of skimmed milk must be removed? So X amount at 0% is going to equal 3.6%, but how much buttermilk do we have? Well, we have 300 minus X amount of buttermilk at 3.6%, which is 0.036. Okay, so 300 times 0.03. Oh, can't see it. Equals 9. Minus 0, so I'm not even going to bother writing it in, right? 9 minus 0 is still going to be 9. But now we need to distribute over here. Let's move my calculator. I don't know, you can't really see it. except for right where I need to, right where I need to work. Okay, let's see here. We'll set it over here. We need to distribute. So 300 times 0.036 equals 10.8. And then I have minus 0.036x. So I'm going to add 0.036x to both sides. And I'm going to subtract a 9 from both sides. Okay, so these cancel, these cancel. I have 0.036x is equal to 1.8, right? 10.8 minus 9 is going to be 1.8. We can double check right here. And then we are going to divide both sides by 0.036. So x is equal to, so let's see, divided by 0.036. X is equal to 50. Now, again, we need to double check. What did we solve for? We solved for the amount of milk being removed. Is that what they wanted to know? How many pounds of skim milk must be removed? Yes, so that's all they wanted to know. So 50 pounds of skim milk is my answer. He's got to remove 50 pounds of skim milk. To get to 3.6%, he'll have 250 pounds of 3.6% butterfat milk, but that's not what they're asking. But, you know, we could find out information like that. All right, so that is mixture problems, okay? Sometimes we're adding, sometimes we're taking away, sometimes we're doing both, all right? If you can set up what's happening, usually you can set up the equations that you need, all right? Go ahead and finish. Like I said, there's a couple pages of these mixture problems. Go ahead and finish those and then meet me back here for our final topic. All right, so on page 48 is our last topic of this section, and it's called work problems. Work problems are quite interesting word problems involving fractions. It says at first the problems may seem impossible, but if you get to the procedures right, they can be a lot of fun. Ooh, we love fun math, right? An important point to remember with work problems is the entire job is represented by the numeral 1, right? One job. Means one job is getting done. Now, there's a lot going on here. I feel like it's quite a bit more complicated than it needs to be, all of this. So we're gonna talk this through, okay? Here is model 1. We are going to take a look at. Mr. Smith can paint the fence around his house in 6 hours. His son would take 12 hours to do the job. If they both work together, how long will they take to paint the fence? All right, so how long will it take them to do it together? Here's how we set up work problems, okay? It is the together over alone plus together over alone equals 1, or as many people that are working as necessary, okay? So to do Mr. Smith, I would set this up, all right? We have Mr. S and we have his son. That's how I would start, okay? Together is the part we're trying to figure out, so that's going to be our X. Mr. Smith can paint the fence on his own in 6 hours. So together is the X. Alone, he can do it in 6 hours. His son can paint the fence in 12 hours. So together is what we're trying to figure out. His son can do it alone in 12. And technically, it's a 1 hour or a 1 full job. Okay. Now we just have, sorry about that. We have 2 fractions plus 1. Or sorry, equal to 1. We're adding fractions. To add fractions, what do we need to have? A lowest common denominator. In this case, it's 12. Now, if we take each fraction and multiply it by 12, we can get rid of the denominators altogether. Not each fraction, but each term, because we don't want to forget the 1. That's what most people do. Don't forget the 1. Okay? 12 times x over 6, right? 6 goes into 6 one time. There are 2 6s in 12, so we end up with 2x. 12 over 12 is 1, so we end up with an x. 12 times 1 is 12. So we have 2x plus x equal to 12, or 3x is equal to 12. Therefore, x is equal to 4. Together, they can paint the house in 4 hours, okay? Now, the book sets up a lot of information here, far, far, far more than we need. This is the part we need to remember. Together over alone plus together over alone equals 1. Okay? That's what we're striving for. Now at the bottom of the page here, it says, although most work problems follow the same format as this one, the placement of the variable changes from problem to problem. Okay? In model 2, you'll find the variable of the denominator of the equation. Okay? So let's turn or take a look at page 49. All right, model 2 here on page 49. It says, when a farmer works with his son, they can plow a certain field in 3 hours. So that's our together, okay? So remember, it's together over alone plus together over alone equals 1. Oh, I wrote that off the screen. There you go. If he is working alone, the farmer will take 4 hours. So we have the farmer and his son, okay? If he is working alone, the farmer will take 4 hours to plow the field. So together they did it in 3, but if he works it alone, it's going to take him 4. The farmer takes 4. How long will it take the son working alone to plow the field? All right, so we know that together they do it in 3, but we're trying to solve for how long the son will take to do it by himself. All right, so our denominator, our lowest common denominator this time is 4x. We're going to multiply every term by 4x. Okay, here the 4's cancel, so we have 3x. Plus, here the x's cancel, so we have 4 times 3, which is 12, equals 4x. 4x times 1 is 4x. Okay, we're going to subtract 3x from both sides. 12 is equal to x. So it's going to take the son by himself 12 hours to plow the field. Okay? I don't really care for the way the book sets it up. This is what we're looking for. Together alone plus together alone equals 1. All right? Let's take a look at the next page here. Okay? So yeah, I mean, this is just telling us exactly what we've already done. So let's take a look at this next page, technically page 50, but when I cleaned up the work that I'd already done here, then I had to erase the page number, but this is technically page 50 here. All right, so at page 50, it says that sometimes workers might be working against each other. Okay, or the things in the problem might be working against each other. So let's look at model 3. A bathtub can be filled with cold water in 10 minutes, but the time will be 20 minutes if the tub is to be filled with hot water. The tub can be drained in 12 minutes if the tub is empty and the faucets are both on and the drain is open. How many hours will the bathtub be filled? So we have 3 things going on here at the same time, and we need to know what is the together. We don't know the together. So we have a faucet number 1, we have faucet number 2, and we have drain. Okay. Now, this is an add, but this is a subtract, right? A drain takes things away. Okay. So the together, we don't know, but faucet 1 fills in 10 minutes, cold water. Plus faucet 2, which is the hot water faucet, we don't know the together, but we know that it could fill the tub in 20 minutes. Now the drain that we're subtracting, okay, it can drain the tub in 12 minutes. We don't know the together, what they do together. So that's why our x's are there. But what is our common denominator? Well, 20 is the largest denominator. So that's where we start. 10 goes into 20, but 12 doesn't. So then we take two 20s, which is 40. Again, 10 is always going to go into that, but 12 doesn't. So then we take 3, which is 60. And we know that 12 goes into 65 times. So 60 is our common denominator, which we are going to multiply every single term by. Do not forget that negative when you multiply. So 10, it goes into 10 once, but it goes into 66 times. So we have 6x. 20 goes into 20 once, but it goes into 63 times, so plus 3x. 12 goes into 65 times, so minus 5x is equal to 60, okay? 6 plus 3 is 9, minus 5 gives me 4x equal to 60. So x is equal to, what is that, 15, all right? So with this faucet running, and this faucet running, and the drain open, the most wasteful bathtub filling in the world, it will take 15 minutes to fill this tub with lukewarm water. Okay, because one's cold and one's hot, right? So lukewarm water. So here's an example of one part of the job working against the job as a whole, all right? So let's do a couple of these problems together, all right? Problem 21. It says Ted can mow a lawn in 5 minutes by using his power mower. So we got Ted. Galen takes 15 minutes to mow the same lawn using a push type mower. How many minutes would the job take if the two boys worked together? So we're looking for the together part, right? So remember, it's together over alone. So Ted can do it in 5. Together over alone, Galen takes 15, and it's equal to one whole job. Okay, my lowest common denominator is going to be 15, so we're going to multiply each term by 15. Do not forget the 1. That's crucial, okay? 5 goes into 15 3 times, so we end up with 3x. 15's cancel here, so I just have a plus x is equal to 15. So 4x is equal to 15. So x is equal to 15 fourths, although we're talking about time here in minutes, right? So we're going to find the improper fraction, which is 3 and, what is that, 3/4 a minute? If they worked together, they could mow this lawn in 3 3/4 minute, which is pretty impressive, honestly. I don't know how big this lawn is, but that's kind of crazy. All right, so that's it. That's our work problem for number 21. Let's take a look at 22, which is on the next page, which would be technically page 51. Okay, at the top of the page here, we see that Mr. Bowl can pick a bucket of apples by hand in 5 minutes. So we've got Mr. Okay. If his son joins him in the work, they can pick a bucket in 3 minutes. How long would it take the son to do the job by himself? Okay, so together is 3 minutes. Mr. Bowl can do it in 5 by himself. Together is 3 minutes. The son, we're trying to figure out how long it will take him to do it by himself. So here's our setup. 3/5 plus 3 over x equals 1. Our common denominator is 5x. So that's what we're going to multiply every term by. All right, 5's cancel, so I have 3x. The x's cancel, so I have 5 times 3, which is 15. And then I have 5x here. So we're going to subtract 3x from both sides. And we get 15 is equal to 2x. Okay, so x is equal to 15 over 2, or 7.5. All right, so the son can pick a bucket of apples in 7.5 minutes. Remember our unit of measure, because we're talking about story problems here. We need a unit of measure. All right, so that's work problems. It is together over alone plus or minus, sometimes together over alone equals 1. All right, sometimes we have something working against us, so it becomes a minus, but this is the basic setup for these work problems. So you've got a couple more practice problems to do, and then that's it. That's the end of this addendum that I put in. I hope you found it as rewarding as I did. As always, if you need any help or have a question, do not hesitate to contact me. Otherwise, until next time.